here. All right. So make sure you get your test back. And overall, really good. I'd say really good test. Pleased. Let's see. Does anyone need the chapter 6 notes from last day? Anyone not here? Make sure we get these. All right. So, got your test back. I posted the solutions on Moodle, so if you have any questions, definitely just ask, and we can sort it out. And if there's trouble with my adding or, well, not subtracting, don't mention that to me, but if there's trouble with my adding, then definitely let me know. We'll take it from there. Oh, if you didn't get assignment 6 last day, I only have the one, so after class I can make photocopies, otherwise it's posted on Moodle, right? And so if you need a copy, then just let me know after class. It is due on Wednesday, so I want to get one of those. All right. Any questions before we start? All right. So last day, we talked about, put this echoey thing over here. Last day, we started chapter 6, and today we're actually just gonna plow through it, because what we noticed was, well, nothing's really changing. We're still doing hypothesis testing. We're still building confidence intervals. The only new thing really is, well, the formulas, but also that we have to check some assumptions before we go ahead and test the hypothesis or do a confidence interval. So what we talked about last day was we just started and we talked about hypothesis testing for one proportion. Where am I? I went the wrong way. And then we went through and did example 2 together just by hand. And I think we got through, yeah, I think we finished, oh yeah, because I think we finished a little early. Or maybe I ran out of time. I can't remember. So a week ago-ish. So we finished hypothesis testing for one sample proportion. So now same deal, we're just gonna keep going and do a confidence interval for one proportion. So remember the sample proportion was p hat, right? So if we know p hat or sample proportion, then as long as we know what confidence level we want, right, we can find our Z star. We know how to find Z star because it's the same Z star that we've been finding all along. And then p hat is the same here, and then q hat, remember, is 1 minus p hat, right? A q is just 1 minus the p over n, which is your sample size. So what's nice about proportions is you don't have to have a lot of information to be able to do these problems, right? And so one thing to notice, though, is that from the hypothesis test, we had Z is p hat minus p naught over the square root of p naught q naught over n. Usually, whatever is down here is what's in the plus minus chunk, right? But that's not the case for proportions, right? So you have to notice that those are different. So you can't just recycle information, right? And so this here and this here, these are different. Just as a heads up, because we have been, for means, right, we were using that little trick where, okay, if we've already calculated it, then we can just reuse it, which we can't do for proportions anymore. P naught, remember, is the hypothesized proportion. So now that I've given you the confidence interval, we can build a confidence interval, and we know how to interpret a confidence interval, right? We use the same kind of blurb, keep in mind that we're talking about a proportion instead of a mean now. Right? So there is example 3, which the solutions are all typed up, but what I'm going to do is, because you can read through those typed up solutions on your own, let's just go and do example 4 together instead. Blah, 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 blah. There's a page in between here. There. So example 4, we can read it. According to a 2012 Bank of Montreal RRSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have a registered retirement savings plan. Now they define RRSP. Weird question, but anyways. A Stats Canada study reported that in 1999, 57% of Canadians had an RRSP. That little fun fact is just thrown in there, and it definitely sets us up for, we can definitely do a hypothesis test for this, but what we're going to do is just do a confidence interval. And so part A says construct a 90% confidence interval for the proportion of Canadian adults who have invested in an RRSP based on this survey. Remembering that we have to check our assumptions now, that's kind of our gateway, and then we can get in and use these formulas, and everything's kind of same, but a little bit different. So for our assumptions, remember our assumptions have 2 parts, and so the first chunk we're going to check regardless of if we're doing a confidence interval or a hypothesis test. So those will be the same regardless. But then the second part is going to change depending on if we're about to do a hypothesis test or a confidence interval. And so what you're going to do, well, on the assignment, you're doing one of each. So you may as well check both assumptions right away. On the final, though, each question is either going to be a confidence interval or a hypothesis test. So then you'll only check the assumptions that apply. Okay? And so that's why you kind of have to keep track of, okay, well, which assumptions do I need for the rest of this question? So read the entire question and just make sure that you're only doing a confidence interval. And so part B, just to make sure that it's not a hypothesis test lurking there, does this provide evidence of a change from 1999 in RRSP investing among Canadians? Left alone, that would be a full-blown hypothesis test, right? Completely fine. But then it says use your confidence interval to test the hypothesis. And so we'll just keep going with our confidence interval. Okay. So our assumptions, the first part, and I like to label the 2 chunks, right? Kind of 2 phases. You don't have to. But the first thing we're checking is independence. The first part of that is, do we have a random sample? And so it doesn't actually say whether the Bank of Montreal collected a random sample, but here's the thing with these assumptions, right, is we're just gonna, it's more about stating things that we're gonna have to assume to go forward, right? So we are assuming that the Bank of Montreal collected a random sample. So the first step is, do we have a random sample? We can assume the sample was randomly selected. if it said in the question, which it might, they collected a random sample of size whatever, then you can just say the sample was randomly selected. Moving on. So the first part is, do we have a random sample? The second part is n less than 10%? So we've got a sample size of 1,000 adult Canadians, let's say 18 years of age or older. Let's just call them adults for simplicity. And so we've got 1,000 Canadian adults. I'm confident when I say that that's less than 10% of all Canadian adults, right? And so we can say something like a sample of 1,000 is less than 10% of all Canadian adults. So that's the first chunk. So you have to check, do you have a random sample? Do you have a sample size that's less than 10% of the population? That's for any sort of question. Now we move on to the normality condition. So normality, we check by, and this is where it differs if we have a hypothesis test or a confidence interval. For a confidence interval, we have to check that n times p hat, which in this case is 1,000 times, and our p hat, let's just write it out here, was 0.67. Even though these values are often given as percentages, proportions are just the decimal version, right? So proportions, when we've got proportions, especially on your formula sheet, right, we have to convert it to proportions to be able to handle it. So p hat is 0.67 and n is 1,000. Just as a side note, the 57% from 1999, so P naught would be 0.57 if we were doing a hypothesis test, comparing 0.67 to 0.57. So n times p hat times 0.67 is 670, which is more than 10 successes. So we can just put a little check mark. Sometimes you'll be given the number of successes. We'll see an example. And then you can just use that, right? Because n times p hat is just the number of successes. And then n times q hat is the number of failures. So n times q hat is 1,000 times, and remember q hat is just 1 minus p hat. So I'll just throw it in there to help clarify some things. 1 minus 0.67 is 1,000 times 0.33, which is 330, which is more than 10. So then we can say something, and this is just for me to show you that, hey, we're done checking assumptions. So therefore, assumptions for inference are satisfied. Okay. Throw in another page here. Oh, wrong page. There. Okay. So now we want to build our confidence interval, right? And so we've got our p hat, I'll just write it down in general, is p hat plus or minus z star times the square root of p hat q hat over n. What do we want to make? We want to make a 90% confidence interval. So we need Z star for a 90% confidence interval. I'll just abbreviate that CI. And then I'll say, using the T table, we find Z star is 1.645, right? Your Z stars are just at the bottom of your T table. But I suspect by now you're pretty comfortable finding T stars and Z stars. So our p hat, remember, was p hat was 0.67. So q hat is 1 minus 0.67, which is 0.33. Now we have all the components and we can just plug them in. Even if you just wanted to plug them in to the formula right away, that's fine too. So now we've got 0.67 plus minus 1.645 times the square root of 0.67 times 0.33 over 1,000. That's your sample size. So if we go ahead and do 0.33, I've got that on my calculator already, so may as well use it, times 0.67. And then I'll just go ahead and divide it by 1,000 right away. Then I get 0.67 plus minus 1.645 times the square root of 3 zeros, 1, 2, 3, and then 2, 2, 1, 1. Don't forget the square root. So if you're working on the assignment and you're getting these huge kind of unreasonable values, then you've probably forgotten to take the square root. Okay. So square root that, or I guess in this case, really small values. 0.67 plus minus 1.645 times 0.014869432 times 1.645. We get 0.67 plus minus 0.02446021. The 0.0244, that's your margin of error. And so remembering that we're still talking about proportions, right? So what it's saying is it's saying 67% plus or minus 2.45-ish percent, right? So if you want to think about it in percentages, that's fine, but we have to deal in percentages, or in decimals for our calculations. So now we can calculate this interval. So I'll store this. 0.67 minus that. I get 0.645539785 up to 0.67 plus that. 0.694460215. I think one of the questions on the assignment, I can't remember which one, but the margin of error is really, really small. So what you'll want to do is you don't want to round until you can't see a difference, right? You'll want to keep as many decimal places as you need to show at what point is there a difference between the two. You'll kind of know what I mean when you get there if you haven't worked on it yet. But just looking at this, if I round to 3 decimal places, that's safe, right? It's showing that, hey, here's the difference between the two, right? And so, or 0.646 up to 0.694. And if you wanted to, you can convert them to percentages, but I'm just going to leave them as they are. Now, as long as we keep in mind that we're talking about the proportion and we're talking about this confidence interval capturing the true proportion, we can interpret the interval. Where is this here? Just so I don't have to. So the question was, construct a 90% confidence interval for the proportion of Canadian adults who have invested in an RSP. So now we made a 90% confidence interval, so we are 90% confident the interval from 0.646 to 0.694 captures, and then whatever I asked you to make an interval for, the proportion of Canadian adults who have invested in an RSP. Who have invested in an RRSP. Ta-da. So part B, or any questions about that first? Kind of same, but different, right? Confidence intervals, interpret them. So part B, does this provide evidence of a change from 1999 in our RSP investing among Canadians? Use your confidence interval to test the hypothesis. So kind of informally, because our interval is going from 64.6 to 69.4, all of that interval, bless you, is above 57%. And so bringing it back down to decimals, since the entire interval is above 0.57, we can conclude does this provide evidence of a change? We can conclude there has been a change. There has been a change in the proportion of Canadians, adults, but I'll leave that because I'm running out of room here. Canadians with RSPs and I'll just add, looks like it has increased. It's asking, has there been a change? It's essentially a two-sided test, right? So we don't actually care, but because this entire interval is above 0.57, then yes, there has been a change and it looks like it's increased. All right. Any questions about that one? Okay. So let's talk about this sample size calculation. You have to do one on the assignment. There's two ways that we can go about doing a sample size calculation. And so we've done one before with the one sample mean sigma known case where we had to calculate the sample size that we would need for some confidence level and margin of error. So the idea is the same now, right? for any confidence interval, we've got the estimate and then plus or minus the margin of error. So now our margin of error is z star times the square root of p hat q hat over n. And so we can say, okay, well, if we let m, lowercase m, be our margin of error, then m is z star times the square root of p hat q hat over n. If we want to solve for n in this formula, then we can just rearrange, and we're left with z star over m all squared times p hat times q hat. And one problem is p hat, right? That's your sample proportion. And when we're trying to figure out what sample size we might need, a lot of the time we don't have a sample proportion, right? We're trying to get a sample proportion, and we're trying to get it to let us estimate with some margin of error to some confidence level, right? And that's kind of cat and mouse here. So what we do is, I'm gonna zoom in here. Instead of using the p hat q hat, which are your sample proportions, which we don't necessarily have, we're gonna use p star q star. So there's p star q star, I know so many p's and q's, on your formula sheet. And p star is the sample proportion p hat, so I'll just highlight this here, where p star is the sample proportion p hat if you know it. So let's say you collect this sample every year, and then we say that we have this preliminary data that we're going to use for our p hat, and that's going to be our p star. Or if you have no idea and you're just setting out to do this study for the first time, you have no preliminary data, then you use a 50-50 split between the two groups. And so then you're going to use just 0.5. And the reason we use 0.5 is a 50-50 split is what's going to give you the biggest possible estimate, right? And so that makes it the most conservative estimate, because while it's going to probably overshoot the sample size you need by a little bit, but we'll do a comparison of the two and notice that it's not actually that big of a difference. So for me, in practice, when I'm telling people how big of a sample size they need, I just use 0.5, right? Just kind of to guard myself against angry researchers. But anyways, so as a rule, I would probably use the 0.5, but you need to know how to deal with, okay, let's pretend that you have this preliminary data, then what are you gonna do? And if you don't have preliminary data, what are you gonna do? And so here I've copy and pasted the question that we didn't do together. It's all typed up, so I said you'll read through it on your own. But we made a 95% confidence interval for the true proportion of students who would choose to do a paired data question. And so what we found was that we have 0.6154, that's our sample proportion, and our margin of error is 0.108, let's say. Okay. And so here's our margin of error with a sample size of 78. So now, what if we wanted to reduce the margin of error to 0.07? Right? So we don't want 0.108 anymore. We want to reduce it to 0.07. How big of a sample size are we going to need? So part A says determine the sample size required using the sample proportion as preliminary data. And I accidentally added another page in here. There. And part B, determine the sample size required assuming you have no preliminary data, right? Which means you're going to use P star as 0.5 and Q star as 0.5. So these ones are typed up. If you're using your sample proportion as the preliminary data, then your P star becomes your P hat, which is 0.6154, right? We're pretending to know something about this population that we're sampling from. We wanted to fix our margin of error to be 0.07 instead of 0.108. That's fine. Z star is still going to be 1.96 for our 95% confidence interval. And so when we do these calculations, we find that we get 185.5593. One important thing is, and we saw this when we were calculating sample sizes before as well, right? We have to round up to 186 because we can't sample 0.5593 of a person, right? Can I just get 0.5593 of your opinion, please? It doesn't really work. And so we always have to round up because even if it was 185.1, we would still have to round up to 186 because even though it would be a very minor change, your margin of error, how it kind of works out in the equation, if you have a sample size that's a little bit smaller than what you need, your margin of error is a little bit bigger than what you wanted, right? And so that's why we have to push it to the full 186. So kind of fun, little sample size calculation. And if we have no preliminary data, right, the only thing that changes is that we have our P star, which is going to be 0.5 now. Right? We have no information about this population. So we're assuming a 50-50 split between the two groups. And same thing here. This just came out to a nice 196, so we didn't have to round because it came to a whole number. So really the difference between knowing something about the population, right, in the first part, where we found a sample size of 186 versus not knowing or pretending not to know anything, 196, that's not a big, I don't know, it's not a big jump, right? And so just to err on the side of caution, I would just say, okay, I'm going to use 0.5 and then get a big sample size, but at least I know it's going to be big enough. Okay. Any questions before we do our example? Oh, do I have any side notes on here? No. If we want to estimate the proportion P with 95% confidence and a margin of error no greater than 3%, what sample size will be required? So this is kind of like bare bones, no other information is given, right? You just want to be able to estimate any proportion P with a 95% confidence and a margin of error no greater than 3%. How big of a sample are we going to need? And so here, we're not pretending to have any preliminary data. And so we want a 95% confidence level. Oops. Which means that Z star is 1.960. I'll jump to the next page here. M is 3%, right? So our margin of error is 3%. But remember, we can't use the percentages, so we have to convert it to a decimal. And so this is 0.03. Before we do any calculations. With no preliminary data, P star is 0.5. So Q star is 1 minus P star, which is also 0.5, right? We're assuming a 50-50 split. Yeah.
When we're answering this question, do you want us to write?
No, because it'll say assume or use the previous question as your preliminary data, or it'll just have no preliminary data. So then you can just say P star equals whatever. Okay, so now we've got N is Z star over M all squared times P star times Q star. Now it's just a matter of plugging in values, right? We've got 1.960 divided by 0.03 squared times 0.5 times 0.5. 1.96 divided by 0.03. I'll write out my answers just so you can check your work. 65.33 repeating times 0.25. Square that. I get 4,268.44 repeating times 0.25. 1,067.11 repeating. We would need a sample size of 1,068, right, rounding up. Must round up. Right. So that goes in general. If you want a 95% confidence level for your proportion, right, and you want a 3% margin of error, regardless of what you're estimating, you need a sample size of 1,068. All right. Any questions about that one?
What would happen if you rounded down? Would it be like?
It's just, I mean, in this case, no, you probably wouldn't notice it until, I would guess, around the 5th decimal or so. It would just make your margin of error a little bit bigger than 0.03. So now, in bumping it to 1,068, our margin of error is going to be a little bit smaller than 0.03. But potato, potato. It's more about the idea of it. Any other questions? Cool. All right. Let's move on to two sample proportions. So for two sample proportions, we have the exact same problem that we had with two sample means. Right now we've got two samples of information, and so that means that we've got a sample proportion for group 1, a sample size for group 1, a sample proportion for group 2, a sample size for group 2, right? We've got information from both groups, and so we need to handle that. We also have to basically double up on our assumptions. And so, but besides that, nothing really changes. I could give you the formulas and you'll probably be able to figure out what to do. One thing though, is that because I was just trying to use up kind of printed paper already, last day I gave you some other formulas or formula sheets that I had left over with the formulas for 6.2, because if you check, you might not have a formula for section 6.2 on here. It's posted on Moodle, so I'm just gonna steal it from here. But make sure, and of course the one on the final that you get, the formula sheet, it'll have it, but just for when you're practicing. Let's just talk briefly about the formulas on the formula sheet, right? So we've got this confidence interval. Hats on top of our P's are just sample proportions, right? And so we've got P1 hat minus P2 hat. Fair enough, right? We're comparing the difference between two proportions. plus minus z star is the same. And then the square root just gets a little bit bigger to accommodate that we've now got 2 p hats and 2 q hats and 2 n's, right? And so this one, the confidence interval, pretty straightforward. Our hypothesis test is always going to be that we're checking, okay, is the proportion of group 1 equal to the proportion of group 2? Same thing as for the means, though I want to see question-specific subscripts here, right? P male equal to P female, for example. And then the default is that they're not equal to, but we can definitely test to see if one's less than the other or one's greater than the other. Our Z that we calculate, here's where things get a little different, but not too bad. We've got our P1 hat minus P2 hat, that's fine. Then we've got just plain P hat, and that's going to come from our pooled proportion. So when we're pooling it, we're just saying, okay, we're going to combine the number of successes over the total number of individuals, right? So your total sample sizes. And so you can calculate it as N1 times P1 hat plus N1 times P2 hat over N1 plus N2. Or if you want, it's also equal to x1 plus x2. Remember, x is the number of successes in each group over n1 plus n2. So those first two are the ones on your formula sheets, right? But you can remember it as x1 plus x2 if you want. For comparing two proportions, usually what I'll end up doing is I'll say 40 out of 100 people said this and 50 out of 150 people said this. Right? Compare those two proportions, and so then you have the successes from each group and your sample sizes from each group. But once you have your p hat, your pooled proportion, then you have your pooled proportion and then your pooled, I guess, anti-proportion. I don't know. Q hat is just 1 minus P hat. So once you've found it, it's just 1 minus that. And then times 1 over N1 plus 1 over N2. So, like I said, update your formula sheets that you're working with for practicing. Or, I don't know, just print off the formula sheet on Moodle. Matter to me. Or if you got that extra last day, then you can cut it, paste it. All right. So like I said, our assumptions, we just have to basically double up because now we've got 2 samples that we need to check. And there's a mega typo and a little typo on here, so stay tuned. We're still going to check independent observations and normality. These assumptions are always going to be the same regardless of if we're doing a confidence interval or hypothesis test, so same deal. But then the normality is going to depend on, are we doing a hypothesis test or a confidence interval? So for the random sample, now we're just saying both samples have to be randomly selected. Crazy, right? And then for the 10% condition, each sample has to satisfy the n being less than 10% of the population condition. And then one that I forgot that honestly isn't that important is that N1 must be independent of N2. Basically saying you can't have people in both groups, right? You either belong in the group 1 or you're in group 2. That's not really going to come up. So I forgot to put it on there, but it should be on there. So that was my little typo. Here's my big typo. for the normality condition, we have to have at least 10 expected successes and at least 10 expected failures, but it should be in each group. And we use the pooled proportion p hat, but if you're looking at this and going, where am I supposed to find my n, right? I've got n1 and n2. Where's the singular n coming from? I have no idea. It was a simple copy paste mishap. So what I'm going to do here is I'm going to just cross this out and rewrite it here. N1 times p hat has to be greater than 10. And N1 times Q hat has to be greater than 10. But also N2 times P hat has to be greater than 10. And N2 times Q hat has to be greater than 10. Otherwise, I don't know where you would find that singular N. Oops. So that's how you check it. If you're doing a hypothesis test. If you're doing confidence interval, then you have to have at least 10 observed successes and at least 10 observed failures in each group. A lot of the time I'll have given you the successes, and so you can just find the number of failures, right? Your total sample size minus the successes. But you have to check it for both groups. All right. Any questions before we do an example?
Yeah. It doesn't meet one of the assumptions. So like, for example, it's less than 10% of the population for group 1.
Yeah.
Just like don't do the question. Or
so here's the thing. So with these assumptions, it's more about stating the assumptions. And so if you're, so in class and on the final and whenever, they're always going to be met, right? So everything's going to be fine. But in real life, if you're doing this and you find, okay, well, I've actually collected more than 10% of my sample, what I'm going to say is there's a chance that the n less than 10% of the population condition is being violated, but I'm going to proceed with caution or something like that. So you just highlight, okay, here's all the things that I'm assuming, and I know I have to check these things. Sometimes we still have to go through and kind of push through. And so you're just going to highlight, okay, I know that this might be going on. And so please interpret these results with a little bit of caution. But good. And you'll see that a lot in StatsCan reports. It'll be like, sample size is less than 20. Please do not make decisions based off of this data and stuff like that. Okay. Good. Any other questions? All right. Cool. So here I've got the general blurbs, but we've already talked about it. So I think we're ready to just jump into our example. And because I was, well, this was last week, but, oh, a surprising. I was rushing to get it to the printers, and so that's why there's just one big example at the end. But it works out because that's kind of all we have time for. So let's do example 7 together, where we're going to do a hypothesis test and a confidence interval. So a surprising number of young adults still live in their parents' home. A random sample by the National Institute of Health included 2,253 men and 2,629 women in this age group. The survey found that 986 of the men and 923 of the women lived with their parents. How large is the difference between the proportions of young men and young women who live with their parents? So far, we're not asking for a hypothesis test or a confidence interval, but what I want to do is just to be aware of what assumptions I'm going to have to check. I'll just read on. So part B, is there evidence that there is a significant difference in the proportion of men who live in their parents' home compared to women? So here we're doing a hypothesis test, and you guessed it, in part C, we're doing a confidence interval. Part C, construct a 90% confidence interval for the difference in proportion of men and women who live in their parents' home. Whew. Okay, so we'll answer part A. Then we're going to check the assumptions for both a hypothesis test and a confidence interval. And then we'll get into doing the hypothesis test. And then finally, we'll end off doing the confidence interval. Okay. I'll just jump down here. So part A. I'm just going to highlight some stuff here that let group 1 be the men. So then X1 is going to be the number of successes. And in this case, because we're interested in, do you live at home or not, right? A success is someone who lives at home. And so we have 986 successes. And our sample size, N1, is 2253. Actually gonna sneak a peek back here, so I don't have to scroll back and forth. So then let group 2 be the women. The number of successes in group 2 is 923, and our sample size of group 2 was 2629. So what we're going to find is we're going to find a sample proportion for group 1 and a sample proportion for group 2. So P1 hat is X1 over N1, which is 986 over 2253, which I'm just working across my page here. 986 over 2253 is 0.437638,704. I'm going to round this to 3 decimal places. If it's important, I'll tell you what to use. So 0.438, and then I'll just make a note to 3 decimal places. So then our P2 hat is X2 over N2, which is 923, whoops, 923 over 2629, which is 0.351084,062, which is roughly 0.351, also to 3 decimal places. So part A, it's just kind of getting us started, right? What's the difference in the proportion? And so P1 hat minus P2 hat, oops, P2 bar. That's crazy. 0.438 minus 0.351. Oops. 0.438 minus 0.351 is 0.087. Same idea as before, right? So we've got this difference in proportion of essentially 8.7%, right? 0.087. So even though it looks small, when you convert it to a percentage, it's not that small, right? But we want to know if it's different from 0. That's going to be the end game. So whenever we're talking about differences, we're going to be comparing the difference to 0. So, but that's part A. How large is the difference between the proportions? 0.087. Moving on. before we go ahead and do part B and part C, we're going to check the assumptions. So check assumptions. There's a lot of them, but like I said before, I'm going to break them up to check the independence assumption and then the normality assumption. So the independence assumption, first one is that we have to have random samples from both groups. And I think it even says, yeah, a random sample by the National Institute of Health included blah, 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 blah. And so the samples, let's make it plural, even though it was just out of one sample and then they split them into males and females. We'll just pretend that those were two individual groups. The samples were randomly selected because it said so. N1 has to be less than 10%. So 2,253, what is it, young adult males? Young adult males is less than 10% of all young adult males. I don't think it even specifies really if it's from one city or one country or, right? But so that's why it's a little bit flexible when, and lets us say, okay, well, then it's definitely less than 10% of whatever you're looking at. Right? We have to check that N2 is less than 10%. And so 2629 young adult females is less than 10% of all young adult females. Wordy, but not hard. And I'll sneak this in too, right? N1 and N2 are independent. Independent. Start over. Independent. Right. The sample of males is going to be independent of the sample of females, or at least that's what we're assuming. Yeah. Okay, moving on to our normality conditions, right? So now we've checked the first chunk that we're always checking, regardless of if we're doing a hypothesis test or a confidence interval. So now moving on to normality. For hypothesis testing, we have to check that N1 times P hat has to be greater than 10. I'll just do it here, do my calculation, because we already found P hat. Or we didn't. Rats. Oh, rats. Okay. Need P hat. P hat is x1 plus x2 over n1 plus n2, which was the 986 plus 923 over 2253 plus 2629. 986 plus 923, 1909 over 2253 plus 2629, 4882 0.391028267, which I'm going to round to 0.391 to 3 decimal places, otherwise it gets a little crazy. All right, now we can check this condition and say, okay, well, N1 times P hat, N1 is 2253 times P hat, which is 0.391. That's going to be 2253 times 0.391 is 880.923. That's greater than 10, so that checks out. Doing the same thing for N1 Q hat. Q hat is 1 minus 0.391. So 2253 times 0.609 times 2253, 1372.077, which is also greater than 10. Great. Do the same thing for our next sample. 2629 is even bigger, right? So it's definitely going to check out, but we still have to jump through this hoop. So 2629 times 0.391, 2629 times 0.391 is 1027.939, greater than 10, and 2 Q hat, 2629 times 0.609, 2629 times 629 times 0.609, 1601.061 is greater than 10. Oops. And now on to our confidence interval. Is your arm sore yet? Confidence interval. Assumption, right? So here we had our, for hypothesis testing, and then because we're about to do hypothesis testing and a confidence interval, we also have to check that. And, or basically, yeah, I'll say N1 P1 hat, which is just X1, which is 986, right? Yeah, is greater than 10. So see how it's a little bit easier? And then N1 times Q1 hat is just N1 minus X1, which is, oops. Right, they're just different ways of writing the same thing. So depending on what information you have, just pick the one that's easier. So it's going to be 2253 minus 986. 1267 is also more than 10. Oops, skip to 10. And 2P2 hat is the same as X2, which is 923, is greater than 10, and N2 times Q2 hat is N2 minus X2, which is 2629 minus 923, 1706, which is also greater than 10. Therefore, assumptions are satisfied. Woohoo. Now that we've checked the assumptions, it's smooth sailing from here, right? Now we're going to do a hypothesis test, and we want to see, are the proportions the same or are they different? I think. Is there evidence that there's a significant difference in the proportion of men? And so part B, step 1 is to state our hypotheses. H naught is that P for the males is equal to the P for the females. Right. Question specific subscripts here. And our alternative hypothesis is that the PM is not equal to the PF, just because we only want to know if there's a difference between the two. Yeah. So now, step 2, do the test. We've done all the hard work. All right, so now our Z is P1 hat minus P2 hat. Oops. Over the square root of P hat Q hat times 1 over N1 plus 1 over N2. Hopefully I have that. Yeah, good. So we had, oh shoot, where do I have it here? We calculated it way at the beginning, but I'll just write it out just so we have it, 0.438 and 0.351. 0.438 minus 0.351 over the square root of, is it 0.391? Is that our pooled proportion? 0.391 times 1 minus, I'll just do it here, 1 minus 0.391, 0.609 times 1 over 2253 plus 1 over 2629. Bring my square root over. Sure, and my fraction. So starting inside the square root, we're just going to kind of build out, being careful that you deal with the 1 over 2253. So 1 over 2253 plus, and then in brackets 1 over 2629. Store that. Store in 1. Okay. 0.438 minus 0.351 is 0.087. So that part's done. Over the square root of, and I'm just going to plow through it here. So I've done the big fractions being added together, and then times 0.609 times 0.391. So I've got the square root of 0.000196264. Square root that, store that. I get 0.087 divided by 0.014009416. 0.087, oh, 0.087 divided by that guy. I get 6.210109086. Remember that we've calculated a Z, right? So Z has to have 2 decimal places. And so we get 6.21 to 2 decimal places. Step 3, find the p-value. If we're thinking in terms of a graph, Z is centered on 0, and we found a Z of 6.21. we know that the area here in the tail is approximately 0. Even though we need a two-sided p-value, right? So our one-sided p-value is approximately 0. Approximately 0 times 2, nothing's really going to change. It's just going to stay approximately 0. So, but what's happening is that we have down here a negative 6.21. We also have approximately 0. So since our one-sided p-value is approximately 0, our two-sided p-value, right? We just take our one-sided p-value, multiply it by 2, 0 times 2, or essentially 0 times 2, nothing's really changes. So our two-sided p-value is also approximately 0. So we've got a two-sided p-value of approximately 0. Step 4 is our conclusion, and our conclusion has always been the same. So since our, not one-sided, our two-sided p-value is approximately 0, it is less than our assumed alpha level, because I didn't give you one to use, and that's okay, is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H0. We have enough evidence to reject H0 in favor of HA. So the question, is there evidence that there's a significant difference in the proportion of men who live in their parents' homes compared to women? Therefore, just rewording it as an answer, there is evidence. There is evidence of a significant difference in the proportion of men and women who live at home. What I'm going to do, because assignment 6 is due on Wednesday, right? And you have to do the confidence interval, even though I'm confident that you can do the confidence interval, I'll just fill in the notes after class now, and then when I post them, it'll have the little confidence interval. So just do it on your own and then check it against mine, make sure it's all good. But otherwise, see you guys on Wednesday. Oh, if you didn't get your test back, come grab it. And if you need an assignment 6, hang back. Oh yeah, you bet. I think you're